So, all right. So, as you remember, in the last class, we were talking about IP related problems and we were on DHCP. So, let's just get back to that slide for a moment. Mm. Oh, just uploaded already. Yeah. If I check here, so we were talking about DHCP in the last class, DHCP relays and DHCP messages and all. Okay, so these are the messages. Just for a quick revision, you can just have a look. Uh, DHCP discover, DHCP offer, request, decline, ACK, negative acknowledgement, DHCP release, and DHCP info. All right. So today we'll see what kind of problems we can face. So we have already discussed about a concept earlier about DHCP which can create problems. You guys remember DHCP snooping, right? So DHCP snooping was discovered earlier. Today we'll see what kind of next problems we can have in DHCP. DHCP troubleshooting issues. But now guys, it depends who is acting as the DHCP server exactly. Who is acting as the DHCP server. So it depends on that who is acting as the DHCP server. Either it is your Windows server or it is your Cisco router, right? Who is exactly acting as the DHCP server? Because like we have discussed, DHCP services are supported by a lot of servers, right? But in DHCP we can have issues. First of all, we have DHCP server configured on Cisco router, let's say. So this is an endpoint, this is an endpoint, this is a switch, and this is a router, right? Then this is the router. So we have two types of scenarios. What are those scenarios? The first scenario is DHCP server is located in the same network. Let's say DHCP server is located here, or even the Cisco router. This Cisco router is configured as the DHCP server. So in this case, we have to see that is this switch has enabled DHCP snooping or not. Because first of all, you have to check the DHCP services must be reaching to this router. The DHCP services must be reaching to this router. If the router is receiving the DHCP discover messages, then you will proceed next. So if we go to the lab, go to the evng. I think the host is reachable or not. Let me check. Server is not reachable, but yeah, on this router, you know that if you talk about Cisco routers are having a very interesting feature of debugging. Have you ever guys used this DHCP debug message or any debug message? Yes. So on Cisco routers, we have debug commands. Let's say if I want to debug DHCP. So basically what debug does, right now I'm having the device access through CLI. So in this CLI, we can say debug IP DHCP server packet. And we can see that is this router receiving the DHCP messages or not. Okay. Debug IP DHCP server packet. Using this message, we can say, okay, if the device is receiving the DHCP messages, then if this user send DHCP discover message received on the router. So if DHCP server is located in the same SAR network, then we don't have to do much about it. First of all, we have to check DHCP snooping is enabled. Yes, DHCP snooping is enabled. So in that case, this interface must be configured as trusted. Then when the messages are going to the router, we'll debug on the router and we see, okay, router is receiving discover message. Router is also giving offer. But before giving an offer, the router is giving an error message sometimes. That error message is because of option 82. So in that case, you have to disable option 82 also. Otherwise, router will keep getting giving the error message and router will not offer an IP address. Router will not offer an IP address. Debug IP DHCP server packets. If the DHCP server is located in a different network, then you remember there are two things we have to check. We have to check two things in this. First, you have to make sure that IP DHCP server or IP DHCP relay agent configuration is there. The command is different, but we have to make sure that the relay agent is configured. So the second scenario could be DHCP server is located in a different network. So if the DHCP server is located in the different network, let's say not even R2, there's R3 who is configured as the DHCP server and the IP address here is 12.1.1.1, IP here is 12.1.1.2, 23.1.1.1, 23.1.1.2. So in this case on R1 we'll go to the LAN side interface, this interface, and we'll run a command IP helper address 23.1.1.2. IP helper address 23.1.1.2. So routing must be configured. So even configuring IP helper address is not enough. This router must have a route in the routing table, because if you look at this, the router does not know how to reach 23's network because it's not directly connected network here. It's an indirectly connected network. So R1 can't reach there. R1 can't reach to that. Uh, yes, Inkosi, you raised your hand. This interface? No, not this. No. Actually, let's say if R2 has a LAN interface here where users are connected. So in that case, on this interface, we have to configure it for these users. But what exactly this IP helper address is doing, it is converting the broadcast messages into unicast. So on this interface, F0/0, we must have an IP address. Let's say this is a LAN subnet 10.1.1.1. So on this interface, we have already configured an IP address. So what this user will do, this user will send a DHCP discover message. The DHCP is based on UDP. So in that case, source port will be 68 and destination port will be 67. Then IP header will be added. But if we would have an IP address, we would not be requesting for the DHCP server. So the source IP is 0.0.0 and destination IP is 255.255.255.255. And then the payload is given to layer 2, the Ethernet. So let's say MAC address is A. So source MAC will be A and destination MAC will be 12 time F, the broadcast. If the destination IP is broadcast, destination MAC will also be broadcast. Once this discover message will reach to the router, what router will do in that case? Router will say, okay, wait, IP helper address is 23.1.1.1. It means that this is the device which can help us to get an IP address. So this router will keep it as it is. It will not make any changes in the DHCP discover message. It will remain as it is. Then source UDP, source port 68, destination port 67. In that case, the source IP will be now 10.1.1.1 and destination IP will become 23.1.1.2. After this, exit interface MAC, because as per the routing, whatever the MAC address of this interface and whatever the MAC address of the next hop, that's the routing purpose. So on the behalf of that, source MAC will be of this exit interface F0/1 and destination MAC will be the next hop. So source MAC and destination MAC will be added, but this is the responsibility of the router to add this Ethernet header. But what this helper address do, it will help us to convert the broadcast message to unicast. Okay, that's why we are configuring it only on this interface. Once the traffic will reach to router 2, R2 will just forward it as a normal IP packet. R2 has no idea is the DHCP discover or what exactly is this message. It just simply forward this message. Okay. Okay. So that's how the helper address is going to help us to convert this message from broadcast to unicast. That's why it's only required on the LAN interface where our user is connected. All right. So now So in that case, if the DHCP server is located in a different network, then we have to make sure what first IP helper address must be configured. Second, a route must be available to reach the DHCP server address. A route must be available to reach that DHCP server. Then, if you have a DHCP server, as you know that on any server, either it is a Windows server, router, or Microsoft server, Linux servers, we always create a DHCP pool, right? So there might be a problem. DHCP server, or you can say DHCP pool out of IP addresses, because you know that whenever we assign an IP address to a host, so on this router, either it is R3 or whoever has configured as the DHCP server, we always create a DHCP pool. And how we created the DHCP pool? Let's say you said pool is 192.168.1.0 slash 28. Let me ask you guys, if I create this DHCP pool, it's slash 28, okay? How many IP addresses this DHCP server can offer? 13? Yeah, but in this, let's say if we would answer this, we can have 14 valid addresses, right? But like you said that also an IP address is consumed by the default gateway. So we can offer 13 IP addresses to the machines. And whenever the router assign an IP address, it always consume, or you can say it always create an entry in the DHCP binding table that okay, this IP address has been assigned and by default the lease time is 24 hours. So a device or a DHCP server is not having infinite number of IP address. A DHCP server is having limited number of IP addresses to offer. So it is very critical for us to make sure that the DHCP pool or the DHCP pool is configured properly. The DHCP pool is having enough IP addresses. The DHCP pool is having enough IP addresses assigned to the users. Otherwise, we'll be running out of IP addresses. Or sometimes we might be attacked by someone, right? Because we can have a DOS attack also, denial of service attack. That's why we have to configure on DHCP. First, we enable the DHCP snooping. Second, we can enable rate limiting, that how many broadcast messages you can send. So that's how we can protect our DHCP server as well from DOS attacks. But we can look for this DHCP pool of out of IP addresses. We might have configured a smaller pool, but later we have realized that we have more number of users. So in that case, we have to change this range or this IP address. We can have chances of misconfiguration as well, because even a small misconfiguration can create a problem. Right, chances of misconfiguration. Let's say we were supposed to configure a pool 192.168.128. Instead of this, you said 127.0/24. So guys, we have to accept this, that we can make mistakes, we can make spelling mistakes, we can make this subnet mistakes also. We can make your misconfiguration. So we always have to keep our mind open that yes, this could be possible. Name is configured differently, IP helper address is misconfigured. There are a lot of chances for misconfigurations. Then duplicate IP addresses. That's why whenever you create a DHCP pool, we always have options to exclude the statically assigned IP addresses. Statically assigned IP addresses. In Cisco routers, we have a command IP DHCP excluded address. IP DHCP exclude addresses. So we can exclude the IP addresses, right, which are assigned statically to the machine, so that these IP addresses will not be offered to any user. IP DHCP excluded addresses. But the question is that how we can detect it, how you can detect the duplicate IP addresses. Yes, guys. How you detect it? Any guesses? By the way, the router, oh sorry, the DHCP server always makes sure that he is not assigning a duplicate IP address. It always makes sure this, or it always tries best that he is not assigning a duplicate IP address to a machine. How? It always generate a gracious app before giving an IP address, right? So whenever this router offer an IP address, before giving an offer, the router always generate a gracious app to check that the IP address is duplicate or not, right? Agree on this? But the question is, let's say router is this R3 and we are requesting an IP address to him. How this router can check the duplicacy, guys? Any guesses? How does router check a duplicacy when it's located in a different network? Because ARP can't be sent. You can't send an ARP request. You can't send an ARP request. So in this case, what this router do, guys? This router will send a ping request. So there are always two methods by Cisco router to follow to check the duplicacy of IP addresses. Either they can check the ping or they can send the gracious ARP. So if the DHCP server is located in the same network, they can send gracious ARP. And if the router is located in a different network, then the router will or the DHCP server will send ICMP echo request to check that the duplicate IP is there or not. Second, you can do one thing. You can have a concept of run a network scan. You can run a command and map, and you can ping the whole IP subnet 192.168.1.0/24. So in this case, you will notice that if two IP addresses are responding for this IP address, then there's a problem because this is a network ID. So either you can ping the network ID or broadcast ID. And if you notice that more than one machines are giving the response of the packet, it means that you are having a duplicate IP addresses. Or we can enable DHCP, this IP source guard. IP source guard can also be enabled on the switch, and that IP source guard can detect duplicate IP addresses. Can detect the duplicate IP addresses. So we have either we can detect it on the basis of ARP table. We can search the MAC address tables not the MAC address but the ARP table, or nmap scan can be done there, or we can check by just normal ping that if you're getting the response, it means that we got a problem and that IP address is not the IP address is duplicate, and this duplicate IP address can also create problems. So we always have to make sure that a server is not assigning duplicate IP addresses to the machines, and this will help us to solve the problems related to the duplication. Okay, guys. Now, and we're talking about DHCP on devices. Let's say we have a Cisco router. So DHCP troubleshooting commands. You can run a command. Let's say this is router 1. You can say show IP DHCP conflict to check is there any conflict with the IP address, the IP which the router is trying to ping. So whenever DHCP server wants to assign an IP address, it always check the duplicacy, and if it gets a response, then that's a problem. So show IP DHCP conflict you can check, or you can say show IP DHCP binding. Using this you can check that these IP addresses are assigned or not. So this command shows us the IP address assigned to the machines, and that IP addresses are, sorry, the client ID also mentioned there, as well as the lease expiry. CIP DHCP binding. Then, as we have already discussed, sorry, this is we are on R2, not on R2. That, let's say it's R1 only. Then again, this is just a router. So on that router, we can say debug IP DHCP server packet, because knowing command is also very important in order to troubleshoot the problem. So IP DHCP server packets. This is a debugging command, and this command is going to detect all the DHCP messages, all the DHCP messages. Yes, please. Till now, if there's any challenge, let me know. Make sense? By the way, most of the time, the Microsoft, or you can say the Windows team or the server team, they handle this DHCP concept. So they handle the DHCP configurations. We are supposed to configure correct helper address, as well as we are supposed to provide IP routing configuration so that the user can reach to the DHCP server, or the request can reach to the DHCP server, so that we can get an offer message, so that we can get an offer message from the server. By the way, in the last class, we were seeing the DHCP configurations, or let's see it quickly here in the packet tracer. We'll just get hands-on experience with the commands. So how many people do we have today? 5. Okay. So let's add an advanced routers. I hope we would be able to run advanced debug commands also. So this is a router. Switch using 1 2. Then let's add one more router here. Host. So we'll just configure one of the router as the DHCP server. We have the IP requirements. So let's say this is R1. On this R1, we'll configure two IP addresses. Configuration mode, hostname R1, interface F0/0, no shutdown. IP address is 10.1.1.1, 255.255.0. And the F0/1 is connected between R1 and R2. So IP address is 12.1.1.1. We can configure /32 as well, because it's a only point-to-point connectivity. Let's configure the IP addresses on the routers first. So on this router, we'll go to the CLI. No. enable configuration mode, hostname R2. Interface F0/0 connected to R1, so 12.1.1.2, no shutdown, exit. Interface F0/1 no shutdown, IP address is 20.1.1.1 It's a LAN subnet, so we've configured /24, and we'll be configuring IP addresses on. Okay, the debug command is not supported for DHCP, no problem. So on this R1, we need to configure routing first so that the DHCP helper address can work. So for routing, I'm configuring OSPF, router OSPF1. Exit, I'll go to the interfaces F0/0 and F0/1 IP OSPF1 area 0, because you know that we can enable OSPF on per interface basis. Router OSPF2 interface range fast Ethernet 0/0, fast Ethernet 0/1, IP OSPF2 area 0. Because you have to make sure that once this user sends a DHCP discover to the router will convert it to unicast. It needs to be reachable to the router. What when this router will give a response, this router also looking for 20's network in the routing table. So that's why whenever you want to implement this, please make sure that routing is configured first. If the routing is not configured, then your DHCP is not going to work. After configuring this routing, show IP OSPF neighbor. Neighborship is coming up, no problem. IP DHCP pool. Let's say LAN 1 network. Now that's a problem. On my LAN, I have an IP subnet of 10, but by mistake, I just configured a network pool with this subnet. So please make sure that the IP subnet is correct, 10.1.1.0. Then default router means the default gateway, 10.1. Let's say DNS server is also required, so 8.8.8 can be configured here. One DHCP pool. Do show history. Likewise, we'll create IP DHCP pool LAN 2 network 20.1.1.0/24 default router 20.1.1.1 DNS server 8.8.8. Do show history. So we have configured two DHCP pools, and we can also verify it from here. Show IP DHCP bindings. There is no binding till now. Show IP DHCP pool. So here we can notice that we have two pool LAN 1, LAN 2. How many IP addresses we have available in this pool? We have 254 IP addresses available. Do we have any leased IP addresses? No. Do we have any excluded addresses? No. So we'll make sure that we exclude the static IPs. Let's say IP DHCP excluded address. In this subnet, I've excluded first 10 IP addresses. That these IP addresses I'm going to use as static. And from the second subnet also I've excluded 10 IP addresses. So you will notice that this router will start giving IP addresses from 11 now. These first 10 IP addresses will not be offered to any DHCP client. If I go to this user desktop IP configuration DHCP, you notice that this user got an IP address 10.1.1.11/24 default gateway DNS server. We go to this user desktop IP configuration DHCP. So this user got an IP address 10.1.1.12 because first 10 IP addresses are right. So we got the IP addresses. 10.1.1.12. But if we go to this users desktop IP configuration, you will notice that they're not getting an IP address. They'll go to APIPA. DHCP field APIPA is being used. Why? Because if we go to the simulation mode, we go to the user desktop IP configuration DHCP. You notice that it's sending a DHCP offer message, sorry, the discover message, but it's a broadcast. Now this broadcast will go to the switch. Switch will forward it to everyone and router and user will discard it. Why? The DHCP server does not have a pool configured for the received port. It drops the packet because this router is not configured as the DHCP server. So we'll go to this router and on this interface F0/1 will say IP helper address. Who can help us to get an IP address? 12.1.1.1. This router can help us to get an IP address. You can configure more than one helper address also. Right, so you can configure more than one helper address as well in case if one of the DHCP server is not responding. So now if we go back to the DHCP, you will notice that the users are getting an IP address. This user is also getting an IP address from this router now. So once we reach to this router, if I show you here, we go to the static, then we go to the simulation mode, and now we request. So in this case, you will notice it will forward this message to the router. The switch will forward it to the user as well, but user will discard this. Now you see what this router is doing. On the left hand side, this shows the message received from the user 0.0.0 and destination IP is broadcast. But what router did? Converted it to unicast. Converted it to unicast. 20.1.1.1 is the source IP and the destination IP is 12.1.1.1. So this is what we do here. We convert this message from broadcast to unicast using the relay agent. And now we notice we go back to this router, show IP DHCP bindings. So we can check these bindings here and show IP DHCP pool. So we have leased two IP addresses. We have leased only two IP addresses because right now we have only two active users. And all of these four entries are present in the DHCP binding as well. Show IP DHCP conflict. So it's not showing any conflict here, right? Because let's say if we connect two more users here and these two users are connected to the switch. Now to this 10.1.1.12 is assigned. So the next IP is going to offer is 10.1.1.13. But what I'm doing here, I'm configuring this IP address as static 255.255.0, 10.1.1 and 8.8.8. So I've configured this IP address as statically here 10.1.1.13. And to this user we'll go and we'll say please offer an IP address. So you will notice that it's going to receive 10.1.1.14. But before that, the router is saying that we have a DHCP address conflict, that we are able to ping 10.1.1.13, that this IP address is reachable. No, this is a normal message without any debug. Okay. Yes, so IP DHCP conflict, and it's going to maintain a database also that these IP addresses are already assigned. So next time we'll not be trying to offer 10.1.1.13 here. Using these techniques, we can troubleshoot DHCP related problems. Sometimes you might face a problem that DHCP server has assigned an IP address, but internet is not working. In that case, you might have configured a wrong default gateway, or you might have configured wrong DNS server also. So that's also needs to be checked. DHCP assigned IP addresses, but the IP addresses must be having a valid default gateway also. Then sometimes the DHCP options mismatch, right? DHCP snooping can also create problems, and all these things we can have in a DHCP server environment. All right, guys. So DHCP play a very important role in a real world, because you know that IP address is like having water, must. Without water we can't survive. Likewise, without an IP address, the machine is of no use, because machine would not be able to send any packets, any data. So that's why having the valid IP address, valid default gateway is very important for a user machine. Only then we can start sending the packets, or we can utilize the network. Otherwise, because we don't have layer 2 protocols for much work, like we cannot access internet using layer 2 packets. That's why it's very important to have a valid IP address from the either the static IP address or from the DHCP server. But having a valid IP address is very important. Having a valid IP address is very important. After that, we have issues with the routing related process. The routing, we have the issues, right? The routing is very important, guys, because we have discussed about the switching behavior. Likewise, we can discuss about the packet forwarding behavior. How many of you know about this packet forwarding process? That what kind of steps a router is going to take in order to forward or in order to process a packet. Let's say this is a router, and this router has two interfaces. Connected to a switch. On this side also it's connected to a switch, and then we have two user machines. We have two user machine on this side also. So this is the interface and this is the interface. This is, let's say, f0/0. This is f0/1. On this interface we have configured an IP address 10.1.1.1/24. So first thing, whenever we configure an IP address on the router, what does this router do, guys? This router maintains the routing table. And in the routing table, the router creates entries for the network 10.1.1.0/24 on this interface and 20.1.1.0/24 on this interface. So we have two interfaces, 10.1.1.0/24 f0/0, 20.1.1.0/24 on f0/1. So we have two interfaces, and on both the interfaces router has IP addresses. Then the router also maintains an ARP table. This is the ARP table. So on this we have two entries by default, 10.1.1. Let's say MAC address is A, MAC address is B. So it will create an entry that MAC address is this on this interface, 20.1.1.1, MAC address is B, f0/1. 20.1.1.1, B MAC address f0/1. This is what a router is going to have by default. Its own IP network and its own entries in the ARP table. Then users are having IP. Either the users are having static IP addresses or dynamic IP addresses, but the users are having IP addresses here, 10.1.1.2/24. Default gateway is 10.1.1.1, 8.8.8. 10.1.1.3/24. The default gateway is 10.1.1.1 and DNS is 8.8.8, let's say. Likewise here, 20.1.1.2/24. Default gateway is 20.1, DNS is 8.8.8. 20.1.1.3/24, 20.1.1.1, and DNS server is 8.8.8.8. Okay, so this is the information we have, right? In this case, the user always sends the traffic to the default gateway, but router always have two types of network, guys, in the routing table. A router always maintain a routing table to store information of directly and networks both. By default, a router does have entries for directly connected networks only. By default, a router does have entries for directly connected networks only. It does not have information for indirectly connected networks. It only know about directly connected ones. And you know that in for indirectly connected network, by default a router does have entries for directly connected networks only. For indirectly connected networks, we have to configure IP routing. But how does a router process the packet? Let's talk about this quickly. So this user, let's say it wants to reach to 10.1.1.2. So first of all, this is an ICMP echo request. ICMP echo request. I will say source IP. Source IP is 10.1.1.1. Sorry, 2, and destination IP is 20.1.1.2. Then the problem is with the source MAC. We have the source MAC AB, let's say so MAC address is CD. So source MAC will be C, but destination MAC is missing. So you guys remember the ARP request behavior. There were two behaviors related to the ARP request. Remember? So if the destination network is in a different network, if the destination is located in a different network, then we are going to do what? We are going to generate an ARP request for the default gateway. So the user will always generate an ARP request for the default gateway. It never know about the different networks. In this case also, let's see if we go back to the network, we go to this host, and from this host, if I ping 10.1.1.12, we are able to ping. 13, we are able to ping. Source IP is 10.1.1, sorry, the ARP entries. Because whenever you reach to different networks, you always send an ARP request for the default gateway. You never know the MAC addresses of the machines. So like in this case also, if you don't know the MAC address of the destination, you're never going to generate an ARP request for that IP. You'll generate an ARP request for the default gateway and you'll get the response A. You'll get the response A. Packet will reach to the router. Packet will reach to the router. This packet always has a TTL value which is not mentioned here, but you guys remember the IP header. TTL value is already there. So this router do what, guys? First of all, the router receives the traffic at the physical layer, because as you remember, the encapsulation works like this, top to bottom, and decapsulation works like this, bottom to top. So first of all, the router will receives the packet on this interface. Okay, received first physical layer, then destination MAC. Okay, destination MAC is mine. Let me open the IP header. Now this router will open the IP header, guys. In the IP header, it will realize that the destination IP is 20.1.1.2. But I just want to tell you one more detail here. Always remember this. Whenever a router receives a packet, it never takes the forwarding decision first, guys. It always decrement the TTL value once. Because now you tell me, okay, yes, say yes or no. If the TTL value is coming to this router is 1, let's say, router has taken the forwarding decisions and traffic is placed on this interface, then router is going to decrement the TTL. So it will realize 1 minus 1 is 0. Does it make any sense to do all this process? So that's why whatever router do, router is going to check the routing table. Yes, no doubt in that. But first of all, it always decrement the TTL value. What if the packet is expired? What if the TTL is 0? Then we are not going to check the route table because it doesn't make any sense. So that's why it's always a better idea to check. So after decrementing the TTL value, it will realize, okay, we can still packet the forward, sorry, we can forward the packet, TTL is not reaching 0. Then it will take a routing lookup. In the routing table, it will realize that, okay, in the routing table, we have the destination IP 20.1.1.2. So the destination IP is not matching in this subnet, but the destination IP is matching in this IP subnet. It means that the packet can be delivered. Destination and packet will reach to the router. Once the packet reaches to this router will say, okay, the destination is matching in this network and it's connected on F0/1. Let me place the packet on this. Now router do what? Router always makes changes, guys. Router is not a transparent device. A switch is a transparent device. Whatever it receives, it forwards. But you know that first thing router decrement is the TTL value. After decrementing the TTL value, once the router is going to place it on F0/0 to F0/1, you know that the layer 2 information is already removed. So you have to rewrite the layer 2 frame. The source MAC is always of this interface B. And for the destination MAC, the router will generate an ARP request. So that's why in the end, you will notice that the router is having ARP entries here. Okay, for 10.1.1.2 MAC is C, and for 20.1.1.2 the MAC is E. If the router is not having the MAC address, router will keep this packet on hold. Sorry, the packet will be dropped and the router will be sending an ARP request tag. Packet will reach to the host. Host will give the response as it is. Then router will take a forwarding decisions, but before that router will decrement the TTL value. And then the router will forward this frame or packet back to this host. So router is never a transparent device. It always makes changes. Like it's not changing the payload, but it's changing the source MAC, destination MAC, plus it's going to decrement the TTL value also. And if it is an IPv4 header, it's going to recalculate the hash as well. You remember the checksum value. So that these are the things a router is going to do once it's forward a packet. So layer 3 forwarding is very interesting forwarding, and the router is always going to check the routing table, and in the routing table we always have this information to forward the traffic. But guys, I'm not sure you guys are aware of this or not, but in a router the routers are using the routing information base, but routing table is not the one which a router use. There's a concept of CEF, Cisco Express Forwarding. A router is always using a concept of CEF in order to forward the traffic. Cisco Express Forwarding. What does the Cisco Express Forwarding do? The Cisco Express Forwarding makes the data forwarding simplest, because forwarding traffic on the basis of the routing table is very CPU intensive, because the routing table is placed in the control plane. So how many of you know about CEF, Cisco Express Forwarding? Okay. So guys, it's not I'll say not the topic of this discussion here, but I would mention it here. The third one is this. Second number, we were having a concept known as fast switching earlier. This is what you learn in CCNP and core. And the first one is process switching. First one is the process switching. So as we were talking about a device is always having three planes: the management plane, the control plane, and the data plane. So this is the data plane. And the physical interfaces, not like a router can have more than two interfaces also, but I'm considering only two of them. Then we have the control plane and we have the management plane here. So the router maintains the routing table, ARP table. All these routing tables and ARP table, they belongs to the control plane. CPU maintains them. So we have the routing table here, and we also have the ARP table maintained by the router. So whenever traffic is received on a device, let's say this is the interface. Packet is received on this interface. This is a packet on F0/0. So this packet will be given to the CPU. CPU will take the forwarding decision on the basis of routing table. It will check the ARP table, it will rewrite the frame, and then packet is given to the interface, and then interface will forward it. So this thing was known as process switching. This thing was known as process switching. Every packet was handled by the CPU. Every packet is handled by the CPU, and it was very CPU intensive. That's why in companies there is a one CEO only, but then chief executive officer, right? Then there are departments. Each department is having their manager, Then inside there, they have specific teams in a department. Then they have a manager. Then they have the employees. Just to make sure that the CEO is not bothered about the basic stuff, right? It's not going to deal with every employee one by one. Just handle high intensive tasks. His job is just to make sure that the company is having projects, budget, everything, right? It's not be bothered about that you need a, let's say, heater, right, in the winters. So he's not there to deal with this stuff. So that's why we always want to offload uh, the traffic from the CPU. That's why we come up with the fast switching. The fast switching is, let's say, okay, we tried our best. We tried to make sure that we can make it simplified, or we can offload the CPU, right? So this was the process switching. But by the way, this is not a topic, guys. I'm just explaining you guys for the better understanding. So this is the process switching here. Every packet is processed by CPU. Then fast switching. So in the fast switching, what we did, let's say we have the same concept. For a moment, let me paste it here. And then we'll move this Ceph here. We need to go to the next page for Ceph, guys. In case of fast switching, what they did, they said that the first packet will go through the CPU, but then we'll create a cache. Okay, that this packet was previously forwarded, and on the behalf of that, a cache will be created, a cache table. So in the fast switching, what we did, we said that the first packet is process switched, and cache entry will be created for later forwardings. But the problem is, whenever you are going to receive a new packet, you always have to go through the CPU. Second, this cache is not upgraded automatically. Let's say if there's any change in the routing table, that change will not reflect in the cache, guys. That's the problem with the fast switching. So always the first packet is going through the control plane. Second, the cache is not dynamic in nature. It always going to be updated manually. Like it's not going to be updated dynamically here. That's a fast switching. It just makes sure that okay, all the packets are not going through the CPU, but again, it's not making much changes here in the CPU utilization. Then what SAF did, Cisco Express Forwarding. Cisco Express Forwarding said that we are not going to have this process switching, Cisco Express Forwarding or fast processing, Cisco Express Forwarding. So the router will maintain the routing table and ARP table. sorry, we have the routing table and ARP table. But in case of SAF, they said very simple concept. They said that, okay, the CPU will maintain all these things, but we will be creating a replica in the data plane. So one thing is known as fib and second is known as adjacency table. And it is always synchronized with the routing table. So fib stands for forwarding information base. Forwarding information base. And then second is the adjacency table. So adjacency table is created with the help of the ARP table and fib is created with the help of the routing table. So then packet will come to the data plane, forward it through the data plane. You don't have to involve the CPU all the time. So this is what SAF is, Cisco Express forwarding. Make sense, guys? Can't get into much details here because that's a CCNP level concept or CCNP topic, but yes, you must know that this such thing exists as SAF. So with the help of the IP routing table, we create the SAF forwarding information base, and with the ARP table, we create the adjacency table. So now we don't need to involve the CPU all the time. Hello. Till now, any challenge here? Any challenge, guys? Please feel free to ask. Make sense? Cisco Express forwarding, forwarding information base, adjacency table, and the routing table. This is known as the SAF. Okay. Let's say on this router, IP SAF. That's how it maintains the entry. The SAF table is more simplified as compared to the routing table. We don't store the codes here and all these extra information that what is the matrix for the routing table and all. And show adjacency. Hope so the command will be supported here. So to check that adjacency table, the command is show adjacency detail. In this case, you will be seeing the MAC addresses information. to adjacency details. That we can check the adjacency table also, guys. But right now, the router is not interested to show us the adjacency table, but it's going to make the process of data forwarding very simplified, and it also decrease the CPU utilization. So you have to make sure that the SAF is enabled on your router. If you see that the CPU utilization is spiking a lot, or you can see that CPU utilization is increasing on the router, so you can check the SAF is